Welcome back to our documentary explainer series, Inside Time Series. Let's just dive right into episode 8, because today we are tackling a massive data mystery. So, if you've been following along with us, you know we've spent a lot of time exploring how data from yesterday helps predict tomorrow. But what happens when tomorrow isn't actually dictated by yesterday, but by the exact same day last year? Well, today we're investigating the seasonal mystery. And this is the central question we really need to answer today. How on earth do algorithms actually anticipate things like incredibly crowded retail stores in December or massive electricity spikes in the middle of summer? How do they know a pattern is repeating? And more importantly, how do they mathematically capture that pattern so they can predict the future? I mean, we see these real-world rhythms literally everywhere we look. Think about it for a second. Retail stores get absolutely slammed every single December. Electricity demand, it goes through the roof every summer the second air conditioners kick on. Website traffic spikes consistently every Monday morning when people get to their desks. We see it in holiday tourist waves, and unfortunately, we even see it in seasonal flu outbreaks. Human behavior and natural phenomena operate in these undeniable, highly predictable cycles. The future, in a lot of ways, really does repeat itself. Now, we previously learned about ARIMA models, right? And they are fantastic at finding linear dependencies in immediate past data. But actually, that's exactly ARIMA's mathematical bottleneck. It only looks at the immediate past. If you're trying to predict retail sales for this December using a standard ARIMA model, it's going to heavily weigh what just happened in November. But November's data doesn't help you much when you're preparing for a massive December holiday rush. ARIMA is essentially blind to recurring seasonal behavior. And that is exactly why we need its more advanced counterpart, SARIMA, which actually learns to look one full season ago. Chapter 2, Teaching AI about Seasons and Building Our Intuition Before We Get into the Heavy Mathematics. So when you look at a time series that has clear cyclical behavior, it's pretty distinct. If you just stare at the raw data, that incredibly jagged, messy line, you'll notice distinct peaks and valleys that just keep repeating over time. This is exactly what monthly home energy consumption looks like, or annual airline passenger data. But here's the thing. To make sense of this for an algorithm, we can't just feed it that raw, jagged line. It's too chaotic. We have to break it apart. We do this by deconstructing that messy reality into 3 distinct layers. First up, we extract the trend, which is just the long-term increase or decrease in the data, kind of like the general rise in global airline travel over a whole decade. Second, we isolate the seasonal pattern, and according to our sources, true seasonality always has a fixed, known frequency, like the 12 months in a year. Finally, whatever is left over is just the noise, those random, unpredictable, day-to-day fluctuations. By peeling the data apart like this, we isolate that underlying fixed seasonal pattern. And this brings us to the absolute core intuition behind how we mathematically model this. It's called seasonal lag. Instead of just looking at what happened yesterday, we are comparing current data to observations separated by one complete seasonal cycle. So to accurately predict this July's airline passenger numbers, we absolutely must look at last July, not just this past June. We literally teach the model to bridge that gap across time. Chapter 3, Inside SARIMA. Let's look at the mathematical engine. Okay, so SARIMA. It stands for Seasonal Autoregressive Integrated Moving Average. Now, I want to be super clear about something right off the bat. SARIMA is not a replacement for ARIMA, not at all. It's more like a really elegant, highly necessary upgrade. It explicitly models these recurring seasonal dependencies by essentially running a secondary model across those seasonal gaps, all while it still maintains the standard ARIMA logic for the short-term, day-to-day gaps. The really crucial point here is how this upgrade works. This seasonal modular upgrade just sits right next to your standard ARIMA parameters, basically like a bolt-on extension. You've got your standard non-seasonal base, the lowercase p, d, and q that represent the autoregressive, differencing, and moving average terms we already know. But then, right next to it, we have the seasonal upgrade, represented by the uppercase p, d, and q, all wrapped up with a lowercase s. And that s, that stands for the seasonal period. Let's actually zoom in on that uppercase D for a second. That stands for seasonal differencing. You know how standard differencing removes a trend? Well, seasonal differencing removes seasonal effects. We literally just subtract the value from one full season ago. So for monthly data with a yearly cycle, we subtract the data from exactly 12 months prior. By stripping away this massive repeating seasonal wave, we reveal the hidden stationary behavior beneath it, and that allows the rest of our model's autoregressive and moving average components to actually do their job properly. Chapter 4, Engineering Seasonal Forecasts. Let's take this from theory over to practice. Remember that little S parameter we just talked about? Well, it is entirely grounded in real-world business calendars. Data scientists and engineers choose this seasonal period based completely on the specific frequency of the data they're handling. If you're predicting daily energy demand using hourly data, your S parameter is 24 because that cycle repeats every 24 hours. For Monday website traffic using daily data, S is 7. For annual airline travel using monthly data, your S is 12. The model completely relies on the human engineer to tell it exactly how wide that seasonal gap is. And because it is so incredibly adaptable, SARIMA has become an absolute industry standard. I mean, it successfully models those massive summer peaks in international flights. Utility companies use it to predict winter spikes in home heating so they don't accidentally overload the power grid. Retailers swear by it for inventory planning, making sure their shelves are fully stocked right before the holiday rush hits. It's even used to predict healthcare demand and flu outbreaks. Whenever the frequency is fixed, SARIMA is just an unbelievably powerful tool. Chapter 5. Beyond Fixed Seasons, the Evolutionary Cliffhanger. But we do have to pose a really crucial question here. What happens when those seasonal patterns actually change? You see, SARIMA's absolute biggest limitation is its rigidity. It firmly assumes that seasonal behavior remains relatively stable and fixed over time. Basically, if a cycle was exactly 12 months long back in the 1990s, SARIMA is going to assume it will behave exactly the same way today. But let's face it, the real world doesn't work like that. The future doesn't always repeat itself perfectly. I mean, what happens when shopping behavior completely shifts from a one-day Black Friday event to basically an entire month of Cyber November? What about massive, unprecedented global disruptions like COVID, or dynamic marketing campaigns, abrupt product launches, or holidays that literally shift dates on the calendar every year, like Easter or Ramadan? These real-world dynamics completely break the rigid, fixed cycles that SARIMA relies on so heavily. Sometimes seasons don't just repeat, they evolve. And that brings us to the next massive leap in our journey. Because when the classical tools just couldn't handle the dynamic, constantly evolving seasonality of the modern internet, the tech giants had to invent something entirely new. Next time on Inside Time Series, we're going to explore why Facebook built an entirely new forecasting algorithm specifically designed for modern businesses. It's called Profit. You absolutely won't want to miss it. See you next time.